Hi everybody, my name is Jared Day and I'm here at Vacuum Interrupters Inc. in Dallas, Texas. Today I'm going to demonstrate our MAC-TS4 vacuum interrupter test set. I'm going to start off with a few slides of theory so everybody's on the same page, and then we'll go into a live demonstration. So start with some slides. So our first slide is, hold on just one second, sorry. I can't see it. Our MAC tester, MAC stands for Magnetron Atmospheric Condition Test Set. So a magnetron is a high voltage crossed with a magnetic field. And then we're trying to determine the atmospheric condition inside of the vacuum interrupter. So a little bit of history on vacuum interrupters. So many vacuum interrupters were installed in the mid-1980s, and many of those vacuum interrupters are still in service today. So they've well exceeded their 20-year shelf life that most manufacturers suggest. The standard test procedure for vacuum interrupters is a high voltage or high pot test, where you increase the voltage to a predetermined set point, and if the vacuum interrupter is unable to insulate the voltage, then it's said to fail. Otherwise, it passes the test. The problem with this type of testing is that it doesn't give you any idea of how close to failure you are, so there's no trendable data that goes along with the high pot test. So our MAC tester is able to actually trend this pressure data. So the internal pressure of the vacuum interrupter is what provides its insulating ability. So it's able to trend this pressure data over time, and we know approximately when these vacuum interrupters fail. So we can give an estimate of when that failure would occur and give you the opportunity to replace the vacuum interrupter before we reach that point. So next slide, please. This is a picture of a standard vacuum interrupter. You've got your fixed and moving copper shafts, and then ceramic insulating the two ends from one another. Inside you have a series of shields and the metal bellows as well. So the purpose of the shields is actually to catch metal vapor when you interrupt current. So if you open the contacts while current is flowing, then you will vaporize a small amount of that metal contact material, and you don't want that material depositing on the inside of the insulating material, because if that were to happen, then you could have an internal short circuit, which would eventually lead to failure. So the materials, the stainless steels, the coppers, everything that is internal to the vacuum interrupter has some gas content inside. So over the life of the vacuum interrupter, these gases will migrate out, being in a vacuum. Also, you have very small molecules like hydrogen and possibly helium that can leak through the materials and small pathways connecting all the parts together. So eventually, all vacuum interrupters fail. Some fail much sooner than others. It's all dependent on the quality of the materials that it's made of and its duty. So the way that vacuum interrupters are tested is what's called a pinning discharge mechanism. So pinning was a scientist who found this effect where if you apply a high voltage and a magnetic field, then you can create a current that is proportional to the pressure inside of the volume. So the higher the pressure, say inside of the vacuum interrupter, the higher the current that you're going to measure. So this is the basis of our MAC test set. So we've got a series of curves that are programmed into the MAC test set, which have these currents and pressure, what we call curves. So we found that the different diameter vacuum interrupters have slightly different curves. So we have 6 generic curves programmed into the MAC test set that show different diameters and have different curves for those different diameter VIs. Go ahead. So, like I said, gas molecules accumulate over the life of the vacuum interrupter. Eventually, enough molecules will have accumulated in the vacuum interrupter where it's unable to insulate the voltage anymore. Go to the next slide, please. So for the MAC test, when we're actually doing this test, we apply a high voltage and we measure the normal leakage current of the bottle, just like you would for a DC high pot test. There's no real effect other than, again, a small leakage current across the vacuum interrupter from the electrons traveling between the contacts. Next slide, please. But if you apply a strong magnetic field while you're applying that high voltage, then those electrons become trapped in the magnetic field and they ionize all the gas molecules inside of the vacuum interrupter. So what this does is it generates electrons, which produces a current, but it also produces a conductive path through the vacuum, which normally there is no conductive path. So the amount of current that flows across this path is directly proportional to the internal pressure. So for reference, this is what's called Paschen's curve. So this is specific for dry air. So you see the dielectric strength or the insulating ability versus the pressure inside of the vacuum interrupter. So on the far left side is very good vacuum, very low pressure. So this is where vacuum interrupters start at approximately somewhere around 1 to the minus 5 Pascal. Over their life, they increase in pressure, so they move to the right on this graph, eventually reaching a point somewhere around 10 to the minus 1 Pascal where the insulating ability drops off very rapidly. So this would be the point at which vacuum interrupters would begin to fail high pot. Somewhere on this falling curve. It varies for different vacuum interrupters and different internal designs. But what we want to do is we want to replace these vacuum interrupters before they reach this point. So manufacturers of vacuum interrupters for a long time have had a upper limit of approximately 1 to the minus 2 Pascal, which is the limit at which we at Vacuum Interrupters Inc. suggest replacing the vacuum interrupter. So you're well before the point of failure, so you can prevent any type of unnecessary damage to the equipment or harm to personnel. So the way that we're able to produce these curves, these current versus pressure curves, is connecting a vacuum interrupter that has a vacuum fitting welded to it. We connect that vacuum interrupter to a high vacuum system capable of pumping it down to new vacuum interrupter levels. So we also have a pressure transducer that's measuring the pressure while we're pumping it. And we also have some insulating links between the vacuum interrupter and the pump, which allows us to apply the high voltage at the same time. So we pump the vacuum interrupter down to again, a new vacuum interrupter pressure. We actually perform the MAC test on it, measure the current, and then vary the pressure all the way to the point where it fails the test. So this is the way that we're able to produce those curves for the MAC test set. Several years ago, we tested a group of vacuum interrupter breakers in Gainesville at our CBS shop. We had over 300 of one type of circuit breaker that they manufactured over a 40-year period. So we went and we took those vacuum circuit breakers and we MAC tested every single VI on all the breakers. And what you see here is a plot of all of the results with the different levels of pressure, so green being good, yellow being mid-range, red being near failure, and gray failing our test. So you also see the age of the breaker on the bottom x-axis. So for very young breakers, you have many good results. 1 to 10 years, many good results. 11 to 20 years, you still see many good results. After 20 years, you see a noticeable decrease in the very good pressures and a jump in the mid-range pressures. But then after 30 years, you see a large increase in the number of high-pressure vacuum interrupters. So this just goes to show that the 20-year shelf life may be a little conservative, but in reality, vacuum interrupters, at least for this particular type, may last around 30 to 40 years, but we're at that point for many of the vacuum interrupters that are in the field today. So now I'm going to go to a live demonstration of our MAC set. Here I've got a VCPW type breaker. This breaker was originally made by Westinghouse, then Cutler Hammer, and now Eaton. So to perform the test, we have our high voltage connections. So red high voltage, black signal return. And then we have our, what we call the universal flex coil. So this is the way that we're able to provide the magnetic field to the vacuum interrupter. This is generic. This goes with every MAC tester. If you can test with the flexible coil, then that's probably the best way to do it here. So for the coil, you want to wrap it at least 5 times around the vacuum interrupter. You also want to insulate it from any type of high voltage. So on these vacuum interrupters, there is a center shield band, which if it's unable to insulate the voltage, then there will be high voltage on this center shield band. So we've wrapped transformer winding paper, Nomex, or some people call fish paper, around the vacuum interrupter first, in case the high voltage can't be insulated by the VI. We're not sending the high voltage back through our magnetic field coil, so there shouldn't be any damage to the test set. If the high voltage does come back through the magnetic field coil, there is a chance that it could fail. So you want to get, again, at least 5 wraps. You want to cinch the coil tightly so that there's no slack, and you don't want the coil to slip down while you're doing the test. So you want the coil centered approximately where the contacts are going to be inside the vacuum interrupter. And just the best practice is to put your high voltage on top and your signal on bottom, just in case there is an accidental movement of the coil and it were to fall down. You don't want the coil to fall down while the high voltage is being applied. So now I'm going to run the test. So this is the main menu of the MAC-TS4. You've got your VI test, which is test setup, any saved data that you've got in here, and then settings and PC connection. You can run this with a laptop or a PC to collect the result directly. So we're going to set up a test. Like I mentioned, there are different curves for the different vacuum interrupters. So you can see the different diameters of the vacuum interrupters and the curve number you should select for that diameter. These are approximately 4.5 inches in diameter, so I'm selecting curve 2. You've got 2 different test voltages here. You've got 25 kV and you've got 12 kV. Just as a rule of thumb, you use 25 kV for anything that has a contact gap greater than 1/4 inch, 12 kV for anything less than 1/4 inch, which generally means that breaker bottles will use the 25 kV and contactor bottles will use 12 kV setting. There are some unique breaker bottles that are much shorter than others, which you would use the 12 kV setting, but those are pretty rare. Then you want to select your coil. So here we're using a flex coil There are other coil options. If you had the vacuum interrupter removed, then we have some fixed coils that you could test in. And then you have the option of putting in a VIID. So this is just a way to recall this data and have a reference. So it could be the breaker type and the phase, or the VI serial number, whatever helps you to identify the test results and the vacuum interrupter. So here we're going to go run a test. So before I get started, I'll explain what's going to happen. We're going to first apply high voltage. You'll see a high voltage light come on, and we're going to be measuring the normal leakage current. So there's no magnetic field being applied. It's just like doing a DC high pot. Then after the high voltage has been applied and the leakage current's measured, it's going to charge a bank of capacitors inside, because we need quite a bit of power to produce a strong magnetic field. Once the capacitors are fully charged, it will apply the high voltage a second time. While the high voltage is being applied the second time, it will discharge those capacitors to the magnetic field coil, which generates the magnetic field. The whole test only takes about 1 minute to run through. So without further ado, we'll get started. So testing. So it's making sure you have a coil connected. Applying the high voltage, you get a direct readout of the voltage that's being applied. And you also get a leakage current measurement. So generally this is very low, and in this case it's 0. If you do get a high leakage current measurement, then that could mean there's some problem, too short of a contact gap, or high humidity, or other problems inside the VI. So it is good to keep a lookout at that leakage current. So we're fully charged. It's applying the high voltage a second time, and now it's discharging to the magnetic field coil. So that was the entire test. So this is a standard test result that you would get out. You have an ion current. So this ion current is a direct measurement of the current across the VI. So this is, if you had a multimeter connected directly in line, this is what it would read. This is a very low current. The lowest limit that we can measure is 10 to the minus 7 amps, which this is almost to that point. So this is a very good pressure result. So 9 to the minus 5 Pascal. This is approximately a brand new pressure. So this VI would have many years of life left in it. That's the basic test for a universal flex coil. The only other thing I have to add is, if in this style of vacuum circuit breaker, we have a little clearance to actually wrap this coil and get between the line to load insulators and the VI. In some cases, the VI is too close to these line to load insulators. And in that case, it is okay to wrap the coil around those line to load insulators as well. But only in that case. If it is possible to wrap directly around the VI, then that's what you should do. So now we have some options that go with our MAC test set. So we have some custom coils for breakers that it's possible to produce a custom coil for. So we have here a GE Power Vac. So the coil, instead of being a flexible coil, is a hard wound coil with a rigid structure. We call these rigid coils. So this saves a lot of time, makes the test extremely easy. Wrapping the coil is usually the most time-consuming part of the test. So I'm going to move my cables over. So with these coils are much larger than our standard coils, which means that we have to provide more power to these coils to produce the same magnetic field for the smaller coils. So we have what we call a capacitor box. So you want to turn the test set off while you're connecting the capacitor box, because it needs to recognize that the capacitor box is connected to give more options on the test setup screen. So now when we turn it back on, we should see CEXT mode in the bottom corner, which means that when we go to our VI test, we have a different set of curves. We also have a different coil option. So in this case, we have the high MVA power vac, PV rigid VIs. So this would be curve 8. So just for reference, low MVA are going to be the smaller diameter VIs, which are about 5 to 6 inches. High MVA are going to be the larger diameter VIs, which are about 8 inches in diameter. So curve 8, our test voltage is going to stay 25 kV. Our coil option has now changed to PV rigid. You can't select any other type of coil unless you have other coil options that you've purchased. And then again, you can put in some type of reference here. It's alphanumeric, so you can put in whatever you'd like. I believe we've got 8 or 9 characters. So this test takes just slightly longer because we have to charge the extra capacitors inside of the external capacitor box. So we're going to run through this test the same. So we're applying the 25 kV. Very low leakage current, like we would expect. So again, this is going to take a little bit longer. When it gets to 350 volts, it will accelerate. So we're going to 700 volts. And your test result. So this test result is mid-range. The pressure is still very good. So I mentioned earlier the lower limit of the current measurement is 1 to the minus 7 amps. The upper limit is 5 to the minus 3 amps, or 5 milliamps. So again, this result is somewhere right in the middle. But again, very good pressure result. So once you have your result, you can save it to the internal memory. If you don't save it, then that result will be lost. You can also print out the result at any time. So if you have saved the result into the test set, then you can go to the main menu under Save Data, and you can pull that same test result back up. You can print it back out if you need. So at this point, are there any questions yet? No questions? Okay. We have our other coil options I can show you. So this would be our fixed coil. So again, most end users wouldn't have a need for a fixed coil because they test the vacuum interrupter while it's still installed in the circuit breaker. However, service shops or OEMs that manufacture vacuum circuit breakers, this would be something that would make testing a lot easier for them. This is what we use in-house. We test every single vacuum interrupter that leaves our facility with the MAC test set. Again. All right, well, I think that's going to be it for today. Thanks everybody for coming and watching. If you have any questions, let us know. And contact info is at the bottom of the screen.